Greetings and welcome back. So, we're at a very exciting juncture in the course because we've spent all this time, maybe a couple of weeks actually, talking about the beautiful notion of update rules. And I've tried to make the argument that this is really participating in a 350-year-old revolution. And in particular, what I mean by that is shown here. I've talked many times about the fact that Newton, in his Principia, when he wanted to describe the orbits of planets, that the way he did it is shown here, which is he imagined the planet would go in a straight line for a little while, a little time delta t. He would compute the impulse and then redirect. So as you go on the next step, and all of that can be summarized by this sort of rule that I show you here, which I'm going to call an update rule, which is a naive version of the Euler forward Euler um, integration, time integration. But what I want to argue now is I want to argue something quite different, and that's the reason I find this to be such an exciting part of the course. And what I mean by that is that I want to talk about a hypothesis for an important missing ingredient in the way we think about dynamics of biological systems. That is to say, that as I'm going to try and illustrate in this brief vignette, there are many examples of biological processes which don't have the character of you start with some initial condition and the system is incremented time step by time step by time step in order to achieve some final state which is really dictated by the initial condition. Instead, what I'm going to say is that this is so-called exploratory and purposeful dynamics. And here I give you a myriad of examples of this kind of dynamics. So I've already mentioned the stuff of T update rules. And to just drive that home, this is a reminder. What I would say is that we have all sorts of different fun, interesting, powerful examples of thing now is thing before plus some correction. So the canonical example, the example of all examples, is F equals ma. But that's one of many. Fourier and his establishment of the heat equation, that's a space-time version of an update rule. But to find out what's going on in space, temperature-wise, now, I look at what was going on in space a time delta t ago, and I update based on the Laplacian. We will not talk about that any further right now. I've spent a lot of time in the course already talking about update rules of the form of the law of mass action and its various variants. For example, we wrote down equations for genetic switches. We wrote down equations for the constitutive promoter. We've talked about the length of flagella. All of these can be couched in that kind of language. I gave several homework problems about population dynamics. And from physics more broadly, perhaps my favorite example of all is Maxwell's equations, which tell us how electric and magnetic fields evolve in space and time, propagating at the speed of light. We know that there is this elegant idea of control theory, which I would look forward to coming back to because I would call that a incremental step towards exploratory dynamics in the sense that it's final state driven or purpose driven. We've talked a little bit about Langevin type approaches. We won't talk for now about Schrodinger's equation, but it's also an example of this kind of thing. And we definitely have, and we'll talk more about entropy increasing dynamics. That's a very interesting paradigm. And then the so-called Turing patterns. But enough of that. So that brings us to where we are. So what I want to do in the coming vignettes is I want to propose a principle, or at least a hypothesis for a principle of biological organization. So in my life, I'm a lover of books. I've spent a lot of time thinking about reading books, sometimes trying to write books, and I think that they're part of what Clifton Fadiman called the great conversation. And it's really interesting to see the way different people try to argue for what is the nature of our study of the living. And I'm of the mind that I'm not really interested in consensus. And what I mean by that is I think it's great that different people write books for freshman biology that are different, or about evolutionary biology that are different, or about quantum mechanics that are different. And here what I'm showing you is this book, Cells, Embryos, and Evolution by John Gerhardt and Mark Kirschner, which is an extremely interesting book because it attempts to, rather than focusing on the myriad of brilliant facts that have been learned in molecular and cell biology over the last, let's say, 60 or 70 years, instead to try to posit certain key principles which preside over those facts. To quote Einstein and Infeld in The Evolution of Physics, this is where the world of phenomena encounters the world of ideas, where one tries to articulate principles. And one of those chapters, chapter 4 in particular, is called The Exploratory Behavior of Biological Systems. And this is really intriguing because what they do in this chapter is something that I think of as being one of the main things we try to do in science, which is to unite apparently disparate phenomena. What I mean by that is, I think, well illustrated by, for example, the phenomenon of interference. If you take off from an airport like the Ben Gurion airport in Israel and have a white right-hand side window seat, when you fly over Tel Aviv down to your right, you'll see a series of jetties, and they're parallel to the beach. And the implication of that is that waves coming from the Mediterranean Sea form diffraction patterns, and you can just see it. You can see the interference very nicely. But we know that the same thing happens with light. We know that the same thing happens with sound waves. And so interference is an umbrella over a whole class of apparently disparate phenomena, which are really not disparate. One of my all-time favorite examples is the phenomenon of allostery, where different categories of macromolecules undergo conformational changes between inactive and active states elicited by the binding of some effector molecule. And what that does is it tells us, as was posited, for example, by Leonid Mirny in a beautiful paper in PNAS, that hemoglobin, for example, on the one hand, and nucleosomes might be thought of in the same breath as the same thing, if you'll allow me to use my air quotes. And I think that's profound. And so here, what Gerhardt and Kirshner are trying to tell us is that a myriad of different examples, such as how it is that the immune system works, how chromosomes are captured by microtubules, the development of vasculature, the connection of neurons, the foraging of animals, all of them can be thought of as examples of this so-called exploratory dynamics. And that's really what our message is here. Now, to try to illustrate this, I want to hearken back to an example that was given to me by Andrew Murray, which I thought was really brilliant. So I was telling him that, I was getting ready to teach freshman biology at Caltech, which is a great privilege and an exciting thing to try to do. And, I think it's a very common thing for us to point the finger and to criticize others and to blame the students or whatever. But I think my job description actually is to take students whose experience of biology has been ruined by AP biology, because, as we like to kid around, they colored mitochondria orange, and to try and persuade them that the study of the living world, regardless of whether some AP biology class was boring, is really quite amazing and quite interesting. And so when I asked Andrew Murray, what should I do in this freshman biology class to try to stimulate young physicists, engineers, mathematicians who, at least at first cut, maybe did not want to take biology? And he said, I think that a really interesting example is to try to tell them how it is that you might go about setting up a railroad between Boston and New York if you were to do it the way a biological organism does it. Okay. So if the top film strip shows you the way this would be done by civil engineers and construction workers and so on, you start in the two cities, track is laid down, the tracks intersect at some point, the same way that the channel was dug between France and England, and it works. That's amazing. On the other hand, if you were to do this using the principles of biological dynamics, exploratory dynamics, what we would do is one of us would sit in New York City, another would sit in Boston, we'd have our team of workers, and we'd say, today, go lay down some track. Go in any direction you want, as long as you don't go in the ocean. Just go ahead and do it. And go lay down 100 miles of track, 200 miles of track. And if you happen to encounter those other people coming from the other direction, yay, that's a win. And if not, just take the track apart and try again. That's it. That is the principle of exploratory dynamics. And what I like, it really makes me think in some ways about the early days of quantum physics, when Niels Bohr apparently told the young Heisenberg and others in Copenhagen that they had to give up on their intuitions, which were born of their everyday experience. Of course, that's true in the context of relativity theory, where, we're used to a world in which v over c, the speed of light, is very small, and so we have no intuition for what happens when the velocities are comparable to that of light. Okay, why do I mention that? Because when we sit and think about the craziness of what I just said, our initial instinct is to focus in on how quote unquote inefficient that would be. And I think the message here is that that demonstrates, in some sense, that our intuition is probably flawed. So I love this example. I think about it all the time. So, there are many examples of this kind of exploratory dynamics, and what I'm trying to do in this first vignette on this new topic of exploratory dynamics is basically just to give you, the listener, and me an opportunity to think about examples of exploratory dynamics. So here, I don't know if we did a good job of making this figure. It's a first attempt, so if anybody has any comments about how to improve it, I'd be very happy to hear them. But the notion here is that the variation is induced by what I'm sort of tongue-in-cheek here referring to as the VDJ generator, which I think of as a series of coin flips, which lead to the choice of different sequences to construct antibodies. And then there's the B cell filter, just as an example, which decides whether or not one discriminates between self and non-self. And so the exploration is the formation of different B cells that harbor different receptors. The selection is on self versus non-self, and if self is selected, the cell is taken out of circulation. Another example, another very important example, is that of protein translation. I think it's really interesting. Probably many of you have seen some of these beautiful and classic videos that are narrated by Julie Theriault that show the processes of the cell. And there's a great one on translation, which I just love watching. And it shows the ribosome encountering an mRNA molecule, and then it shows the rhythmic succession of addition of more and more amino acids. And I don't want to say a flaw with the video, but something that we should think about is that in that video, most of the amino acids that arrive at the ribosome are correct. In other words, they go in and they're added. But we know that there's a huge excess of incorrect to correct amino acids, or tRNAs. And so what we're trying to illustrate here is that the variation is in the form of the arrival of tRNAs, and which tRNA is the right one is decided by a daemon. I'm not going to go into that right now, but you might think of that as in the language of kinetic proofreading. I happen to find it interesting to try to connect with the notion of Maxwell type daemons. And so there's variation in selection. Selection means that the daemon decides that the amino acid or the tRNA that's arrived is correct, and the door is open, and then it participates in translation. Another example, I'm not going to comment on this other than to point it out for listeners so that you go take a look at the paper. And I think really in some ways the title says it all. So this is from Joe Howard's group, also work with UHI 2, people that I borderline idolize. Maybe that sounds overly strong, but I very much want to participate in seeing the positives. I just made a quip the other day with one of my friends at Caltech saying, I'm not that interested in, this is a bit of a joke, but I'm not that interested in being a critical reader of the literature. I want to be a joyful reader of the literature, and I want to like things. And so in this case, the fact that the title features the notion of dynamic instability of dendrite trips is awesome. And why I say it's awesome is because that's that unity that I was talking about earlier, that somehow this notion of dynamic instability is a reflection of an underlying exploratory dynamics. In this case, it's not microtubules, but it's rather these actual dendrite tips that are doing the exploratory behavior. Oops, that was not good. So that basically summarizes what I want to say. So just to give you the essence of it, what I wanted to accomplish here was to argue that we have had 350 years of this amazing version of dynamics, which, in sort of modern parlance, if I were to teach mechanics myself, Nani Kondev and I have talked about this before, if either of us, if we were to teach mechanics, either undergrad or grad mechanics, we would not do it in the classic sense that we're all used to, meaning the usual stuff of coupled vibrations, of Hamilton's equations, etc. I love that. That's great. I would definitely do that. But instead, I would really, really try to cast the subject as dynamical systems and update rules. So we have centuries of that, the power of that. And I think it's represented beautifully in Steve Strogatz's book, which I recommend to everyone. That being said, I think that there's a whole host of phenomena where it's more convenient to abandon that point of view and to think instead about what will be the mathematics of trying to think about exploratory behavior. And that's what our next vignette will focus on. The point of this one was to introduce the idea of exploratory dynamics. I hope that this playful example from Andrew Murray illustrated it. I think this is what you should keep coming back to. And if you have your doubts about it, then go look at a movie of the dynamic instability, such as one taken for I think you can find these maybe with the videos for essential cell biology. There's a video by Tony Hyman. There are some by Tim Mitchison. The point is, what you'll see is microtubules growing and shrinking, growing and shrinking, growing and shrinking. In some sense, quite analogous to the picture that I show here. So the message I wanted to get across is a hypothesis. I'm enthusiastic about the hypothesis. How enthusiastic? Committing my time to it and my research time and that of my group members and my friends. So I'm very enthusiastic about it. I think it offers possibilities for thinking about biology in ways that we have not thought about before. And what we'll do in the next vignette is talk about how to mathematicize those ideas.